Right now, wherever you are, you exist at a very specific point in the universe. This point is not random. It is part of a vast structure that extends in all directions, and understanding where you are begins with the simple act of looking around the space you currently occupy. The room you might be in, or the outdoor space where you find yourself, sits on the surface of Earth. This surface is solid beneath you, and it feels still, but that stillness is an illusion created by your scale and perception. You are in fact moving in multiple ways simultaneously, though you cannot feel any of them. This is because everything around you moves together with you, creating the sensation of being motionless. Beneath your feet, the Earth rotates. This rotation happens around an imaginary line called the axis, which runs from the North Pole to the South Pole. The planet completes one full rotation approximately every 24 hours. At the equator, this rotation carries you eastward at roughly 1,000 miles per hour. If you are closer to one of the poles, your speed is somewhat less, but you are still moving. You do not feel this movement because the atmosphere moves with you, and everything you see around you moves at the same rate. While the Earth rotates, it also orbits the Sun. This orbit is not a perfect circle, but rather an ellipse, which is a slightly stretched circle. The Earth travels along this elliptical path at an average speed of about 67,000 miles per hour. This seems extraordinarily fast, but the orbit is so large that it takes an entire year to complete one journey around the Sun. The distance Earth travels in this orbit is approximately 584 million miles. Despite this tremendous speed and distance, you feel no sensation of movement, because once again, everything in your reference frame moves together. The Sun itself is not stationary. It moves through space, carrying Earth and all the other planets with it. The Sun orbits the center of the Milky Way galaxy, which is our home galaxy. This orbit takes the Sun, and therefore us, through space at roughly 500,000 miles per hour. The path around the galactic center is immense, so vast that one complete orbit takes approximately 225 million years. This period of time is sometimes called a galactic year or cosmic year. As the Sun moves around the galaxy, it also moves up and down through the galactic plane. The Milky Way is shaped somewhat like a disk, with a central bulge and spiral arms extending outward. The Sun oscillates above and below this disk as it travels, like a gentle wave motion superimposed on its circular path around the galactic center. This up and down motion takes about 64 million years to complete one full cycle. The Milky Way galaxy itself is in motion. It moves through space as part of a larger structure called the local group, which is a collection of galaxies bound together by gravity. Within the local group, the Milky Way and the Andromeda galaxy, our nearest large galactic neighbor, are actually moving toward each other. This approach happens at about 70 miles per second. In roughly 4.5 billion years, these two galaxies will begin to merge, creating a new, larger galaxy. The local group, in turn, is being pulled toward an even larger structure, called the Virgo supercluster. This supercluster contains thousands of galaxies, and the gravitational influence of all this mass draws our local group toward it at hundreds of miles per second. Beyond that, the Virgo supercluster is part of an even larger structure called Laniakea, which contains approximately 100,000 galaxies and spans 520 million light-years. All of these motions are happening right now as you rest in your current position. You are moving with the rotation of Earth, moving with Earth's orbit around the Sun, moving with the Sun's orbit around the galactic center, moving with the galaxy's motion through the local group, and moving with the local group's motion through larger cosmic structures. Yet you feel perfectly still. This sense of stillness is what allows you to relax and observe the universe from your particular vantage point. You are not fighting against these motions. You are part of them, carried along in a cosmic dance that has been ongoing for billions of years and will continue for billions more. From where you are right now, If you could look up through any barriers like ceilings or clouds, you would see the sky. During the day, the sky appears blue because of the way Earth's atmosphere scatters sunlight. The atmosphere is a thin layer of gases that surrounds the planet, held in place by Earth's gravity. This layer is only about 62 miles thick if we consider the major portion where weather occurs and where most of the air exists. Beyond that, the atmosphere gradually fades into the vacuum of space over several hundred miles. The blue color of the daytime sky comes from a process called Rayleigh scattering. Sunlight contains all colors of the visible spectrum, and when this light enters the atmosphere, it collides with molecules of nitrogen and oxygen. Blue light has a shorter wavelength than red light, and these shorter wavelengths are scattered more easily by the atmospheric molecules. This scattered blue light comes at you from all directions across the sky, which is why the entire sky appears blue rather than just the area around the sun. At night, when your part of Earth faces away from the sun, the sky becomes dark, and if conditions are right, you can see stars. These stars are other suns, located at vast distances from our own sun. The nearest star to us after the sun is Proxima Centauri, which is about 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second. This means Proxima Centauri is roughly 25 trillion miles away. The stars you see at night are at many different distances. Some are relatively close, perhaps just a few dozen light-years away. Others are hundreds or even thousands of light-years distant. All of them are part of our Milky Way galaxy. When you look at the night sky with your unaided eye, every single star you see is part of our galaxy. The Milky Way contains between 100 billion and 400 billion stars, and our Sun is just one of them, located about 26,000 light-years from the galactic center. If you are in a location with very dark skies, far from city lights, you might see a faint milky band of light stretching across the sky. This is the combined light of millions of stars in the disk of our galaxy, too far away and too dim to see individually, but together, creating a soft glow. Ancient peoples around the world noticed this band and created stories about it. The name Milky Way comes from Greek mythology, but many cultures had their own names and interpretations. From your current position, the universe extends in all directions. If you could mark your exact location and then expand your awareness outward in perfect spheres, you would encounter different cosmic structures at different distances. Close by, within a few thousand miles, you would find the International Space Station orbiting Earth, along with numerous satellites that humans have launched for communication, weather monitoring, navigation, and scientific research. Farther out, at about 239,000 miles, you would reach the Moon, Earth's only natural satellite. The Moon orbits Earth approximately once every 27.3 days. It is the brightest object in the night sky and the only celestial body beyond Earth that humans have physically visited. Between 1969 and 1972, 12 astronauts walked on the lunar surface during the Apollo missions. The Moon affects Earth in several ways. Its gravitational pull creates the ocean tides, causing the water level to rise and fall along coastlines twice each day. The Moon also stabilizes Earth's axial tilt, which helps maintain relatively stable climate patterns over long periods of time. Without the Moon, Earth's tilt would vary more dramatically, potentially leading to extreme climate fluctuations. Moving outward from the Moon, the next significant objects you would encounter are the other planets of our solar system. The solar system is the collection of planets, moons, asteroids, comets, and other objects that orbit our Sun. There are 8 recognized planets divided into 2 groups based on their composition and characteristics. The inner planets, also called terrestrial planets, are Mercury, Venus, Earth, and Mars. These planets are relatively small and have solid, rocky surfaces. Mercury is the closest planet to the Sun, orbiting at an average distance of about 36 million miles. It is a small, heavily cratered world with extreme temperature variations, baking hot on the side facing the Sun and freezing cold on the dark side. Venus is the second planet from the Sun, orbiting at about 67 million miles. It is similar in size to Earth and is sometimes called Earth's sister planet because of this similarity. However, Venus is dramatically different in other ways. Its atmosphere is extremely thick, composed mostly of carbon dioxide, creating a runaway greenhouse effect that makes Venus the hottest planet in the solar system, with surface temperatures around 860 degrees Fahrenheit. The atmospheric pressure on Venus is 90 times greater than Earth's, equivalent to being deep underwater on Earth. Earth is the third planet, orbiting at about 93 million miles from the Sun. This distance is often called one astronomical unit, and it serves as a convenient measuring stick for distances within the solar system. Earth is unique in the solar system because it has liquid water on its surface and, as far as we know, is the only planet that harbors life. Mars is the fourth planet, orbiting at about 142 million miles from the Sun. It is roughly half the size of Earth and has a thin atmosphere composed mostly of carbon dioxide. Mars appears reddish because its surface contains iron oxide, which is essentially rust. The planet has polar ice caps, vast canyons, extinct volcanoes, and evidence that liquid water once flowed on its surface billions of years ago. Between Mars and the next planet, Jupiter, lies the asteroid belt, a region containing millions of rocky objects ranging in size from small boulders to bodies hundreds of miles across. The largest object in the asteroid belt is Ceres, which is about 580 miles in diameter and is classified as a dwarf planet. The asteroid belt represents material that never coalesced into a planet, likely because Jupiter's strong gravity disrupted the formation process. Jupiter is the fifth planet and the first of the outer planets, also called gas giants. It orbits at about 484 million miles from the Sun, which is about 5 astronomical units. Jupiter is enormous, more than 11 times Earth's diameter and more than 300 times Earth's mass. In fact, Jupiter is more massive than all the other planets combined. It is composed primarily of hydrogen and helium with no solid surface. If you could somehow travel down into Jupiter, the atmosphere would gradually become denser and hotter until the pressure was so intense that the hydrogen would transition into a liquid metallic state. Jupiter has at least 95 known moons, with the 4 largest discovered by Galileo in 1610. These Galilean moons are Io, Europa, Ganymede, and Callisto. Europa is particularly interesting to scientists because beneath its icy surface appears to be a global ocean of liquid water, making it a potential location where life might exist. Saturn is the 6th planet, orbiting at about 890 million miles from the Sun. It is famous for its spectacular ring system, which is composed of countless particles of ice and rock, ranging in size from tiny grains to house-sized chunks. These rings extend outward from the planet for hundreds of thousands of miles, but are remarkably thin, in some places only about 30 feet thick. Saturn, like Jupiter, is a gas giant composed mostly of hydrogen and helium. It has at least 146 known moons, including Titan, which is larger than the planet Mercury and has a thick atmosphere and lakes of liquid methane on its surface. Uranus is the 7th planet, orbiting at about 1.8 billion miles from the Sun, or about 19 astronomical units. Uranus is an ice giant, smaller than Jupiter and Saturn, but still much larger than Earth, with a diameter about 4 times Earth's. It is composed primarily of water, methane and ammonia ices surrounding a rocky core. Uranus has a peculiar characteristic. Its axis of rotation is tilted so far that it essentially rolls along its orbital path, with its poles taking turns pointing toward the Sun. This extreme tilt may have resulted from a collision with another large body early in the solar system's history. Neptune is the 8th and most distant planet, orbiting at about 2.8 billion miles from the Sun, or about 30 astronomical units. Like Uranus, Neptune is an ice giant with a composition of water, methane, and ammonia. Neptune has the strongest winds in the solar system, with speeds reaching over 1,000 miles per hour. It has at least 16 known moons, with Triton being the largest. Triton is unusual because it orbits Neptune in the opposite direction to the planet's rotation, suggesting it was captured by Neptune's gravity rather than forming alongside the planet. Beyond Neptune lies a region called the Kuiper Belt, similar to the asteroid belt but much larger and more distant. The Kuiper Belt contains thousands of icy bodies, including several dwarf planets such as Pluto, Haumea, and Makemake. Pluto, once considered the ninth planet, orbits at an average distance of about 3.7 billion miles from the Sun. It is a small, icy world with a diameter of about 1,400 miles, smaller than Earth's moon. Pluto has 5 known moons, the largest being Charon, which is about half Pluto's size. The Kuiper Belt extends from about 30 astronomical units out to roughly 50 astronomical units from the Sun. Beyond the Kuiper Belt lies an even more distant and mysterious region called the Oort cloud. The Oort cloud is thought to be a vast spherical shell of icy objects surrounding the entire solar system. It begins at about 2,000 astronomical units from the Sun and may extend as far as 100,000 astronomical units, nearly halfway to the nearest star. The Oort cloud has never been directly observed, but scientists infer its existence from the behavior of long-period comets, which appear to originate from this distant region. Comets are icy bodies that develop bright, streaming tails when they approach the Sun. As a comet gets closer to the Sun, the solar radiation heats the ice, causing it to sublimate directly from solid to gas. This gas, along with dust particles, streams away from the comet, pushed by the solar wind and radiation pressure, creating the characteristic tail. The tail always points away from the Sun, regardless of the comet's direction of travel. The entire region from the Sun out through the Oort cloud comprises our solar system. This system exists within interstellar space, which is the vast expanse between star systems. Interstellar space is not completely empty. It contains extremely diffuse gas, mostly hydrogen, at an average density of about 1 atom per cubic centimeter. It also contains cosmic rays, which are high-energy particles traveling at nearly the speed of light, and magnetic fields that thread through the galaxy. From your position right now, all of this exists around you in 3-dimensional space. The Sun is in one direction, about 93 million miles away. The Moon might be visible above you, or it might be on the other side of Earth depending on its phase and the time of day. The planets are scattered along the ecliptic plane, which is the flat disk where most solar system objects orbit. Some might be visible in your sky, appearing as bright points of light that don't twinkle the way stars do. Planets appear steady because they are much closer than stars and present a small disk rather than a point of light, which makes them less susceptible to atmospheric turbulence. The stars you see are scattered through 3-dimensional space around the solar system. Some are above the plane of our galaxy's disk, some are below it, and many lie within the disk itself. The constellation patterns we recognize are purely the result of our viewing angle from Earth. Stars that appear close together in the sky may actually be vastly different distances from us, having no physical relationship to each other. They simply happen to lie along similar lines of sight. Constellations are human constructs, patterns we have imagined by connecting stars that appear close together in the sky. Different cultures throughout history have created different constellation patterns from the same stars, seeing their own mythological figures, animals, and objects in the heavens. The constellations recognized by modern astronomy are based primarily on Greek and Roman traditions, though they have been standardized and expanded to cover the entire celestial sphere. The celestial sphere is an imaginary globe surrounding Earth, upon which all celestial objects appear to be positioned. Of course, objects are actually at vastly different distances, but for purposes of mapping the sky, we can treat them as if they are all stuck to this imaginary sphere. This sphere appears to rotate around Earth once per day because of Earth's rotation, causing stars to rise in the east and set in the west, just as the Sun and Moon do. If you were to watch the night sky for several hours from your current location, you would see this apparent rotation. Stars would trace curved paths across the sky, all centered on a point called the celestial pole. In the northern hemisphere, this point is very close to the star Polaris, also known as the North Star. Polaris appears to remain stationary, while all other stars circle around it, because Polaris lies almost directly above Earth's North Pole. In the southern hemisphere, there is no bright star marking the south celestial pole, but the same rotation occurs around that point. This rotation of the celestial sphere is one of the most fundamental observations you can make from where you are. It connected ancient peoples to the cosmos and helped them develop calendars, navigation techniques, and an understanding of their place in space. The regularity of this rotation provided a reliable clock and compass before modern technology existed. As Earth orbits the Sun, the night side of Earth faces different directions in space throughout the year. This means that different stars are visible at different times of the year. In 6 months, Earth will be on the opposite side of its orbit, and the night sky will show stars that are currently hidden behind the Sun. This gives us changing seasonal skies, with certain constellations associated with particular times of year. The Sun's apparent path across the background stars, as seen from Earth, traces a line called the ecliptic. This is actually the plane of Earth's orbit, projected onto the celestial sphere. The zodiac constellations are those that lie along this ecliptic path. As the Sun appears to move through the zodiac over the course of a year, the Moon and planets, which orbit close to the same plane, also appear to move through these same constellations. From your position, the universe has a structure that becomes apparent through patient observation. Close by, within a few light minutes, are the Moon and Sun. Within a few light hours are the outer planets. Within a few light days is the edge of the solar system. Within a few light years are the nearest stars. Within hundreds of light years are the stars you can see with your unaided eyes. Within thousands of light years is the local spiral arm of our galaxy. Our galaxy, the Milky Way, has a spiral structure with several major arms and minor arm segments. The Sun is located in a minor arm or spur called the Orion Arm, positioned between two major arms, the Perseus Arm and the Sagittarius Arm. This location, about 26,000 light-years from the galactic center and within the disk of the galaxy, gives us our particular view of the universe. When you look toward the constellation Sagittarius, you are looking toward the center of our galaxy. This region of the sky appears particularly rich with stars because you are looking through the densest part of the galactic disk. At the very center of the Milky Way lies a supermassive black hole called Sagittarius A/, with a mass equivalent to about 4 million suns. This black hole is surrounded by a dense cluster of stars, gas and dust, but the center is obscured from visible light observation by intervening dust clouds. Astronomers study the galactic center using radio waves, X-rays, and infrared radiation, which can penetrate the dust. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. Once it crosses a boundary called the event horizon. They form when massive stars collapse at the end of their lives, compressing their mass into an infinitely small point called a singularity. Despite their name, black holes are not holes in space, but rather extremely dense objects with enormous gravitational influence. The supermassive black hole at our galaxy's center has been there for billions of years, and its gravity helps hold the galaxy together. Stars near the galactic center orbit this black hole at tremendous speeds, and by tracking their motion, astronomers have been able to determine the black hole's mass and location with great precision. When you look away from the galactic center toward constellations like Perseus or Auriga, you are looking outward through our local arm toward the outer regions of the galaxy. In these directions, you see fewer stars because you are looking through less of the galactic disk. If you look perpendicular to the galactic plane toward the constellation Coma Berenices or Sculptor, you are looking out of the galaxy into intergalactic space, where far fewer stars are present and distant galaxies become visible. These distant galaxies appear as faint, fuzzy patches of light, even through powerful telescopes. They are island universes, each containing billions or trillions of stars, located millions or billions of light-years away. The nearest major galaxy to the Milky Way is Andromeda, which is about 2.5 million light-years distant. On a dark, clear night, Andromeda is visible to the unaided eye as a faint, elongated smudge in the constellation Andromeda. This smudge is actually a galaxy larger than our own, containing perhaps 1 trillion stars, seen from a distance of 25 quintillion miles. The light you see when you look at Andromeda left that galaxy 2.5 million years ago, when early human ancestors were just beginning to appear on Earth. You are seeing Andromeda as it was in the distant past, not as it is now. This is true for everything you see in the night sky. The light from the stars took time to reach you, so you are always looking back in time when you observe the cosmos. The nearest star, Proxima Centauri, shows you what was happening there 4.24 years ago. More distant stars show you the past from decades, centuries, or millennia ago. Some of the stars you see may no longer exist, having exploded or faded since their light began its journey to Earth. Conversely, many stars have been born in the time their light has been traveling, but you cannot see them yet because their light has not reached Earth. This light travel time effect means that the universe you observe is not the universe as it exists right now, but rather a collection of images from different moments in the past, all arriving at your eyes simultaneously. The farther you look into space, the farther back in time you see. This principle allows astronomers to study the history of the universe by observing distant objects. The most distant objects we can observe are so far away that we see them as they were billions of years ago, when the universe itself was much younger. The current record for the most distant observed galaxy places it at a distance where we see it as it was just a few 100 million years after the Big Bang, which occurred about 13.8 billion years ago. The Big Bang is the name given to the event that marks the beginning of the universe as we understand it. This was not an explosion in space, but rather an expansion of space itself. At the earliest moments we can describe with current physics, the entire observable universe was compressed into an extremely hot, dense state. Time and space as we know them began at this moment. As the universe expanded, it cooled, allowing energy to condense into particles, which eventually formed atoms, which eventually collected into stars, galaxies, and all the structures we observe today. The evidence for the Big Bang comes from several independent observations. First, we observe that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This expansion was discovered in the 1920s by Edwin Hubble, and it suggests that in the past, everything was much closer together. Second, the universe is filled with a faint glow of microwave radiation coming from all directions, called the cosmic microwave background. This radiation is the cooled remnant of the intense heat from the early universe. Third, the observed abundances of light elements like hydrogen and helium match the predictions of Big Bang nucleosynthesis, the process by which these elements were created in the first few minutes after the Big Bang. From where you are right now, this cosmic microwave background radiation is passing through you constantly. It is too faint to see or feel, but it is there, a whisper from the birth of the universe arriving from all directions. This radiation has been traveling for nearly 13.8 billion years, cooling as the universe expanded, until now it has a temperature of about 2.7 degrees above absolute zero. The observable universe, which is the part of the universe from which light has had time to reach us since the Big Bang, is enormous. It extends approximately 46.5 billion light-years in all directions from Earth, giving it a diameter of about 93 billion light-years. This is larger than you might expect, given that the universe is only 13.8 billion years old, because the universe itself has been expanding during the time light has been traveling. Space itself stretched while the light was in transit, carrying distant objects farther away. Everything you can observe, even in principle, lies within this observable universe. Beyond this boundary, there may be more universe, but its light has not had time to reach us yet. The universe may be infinite, or it may be finite, but unbounded, like the surface of a sphere. We do not currently know which is the case, and we may never know with certainty. The observable universe contains an estimated 2 trillion galaxies, each with millions, billions, or trillions of stars. The total number of stars in the observable universe is estimated to be around 1 septillion, written as 1 with 24 zeros after it. Among all these stars, many have planets, and among all these planets, Earth is the only one we know with certainty harbors life. From your current position, you are part of an unbroken chain connecting you to the earliest moments of the universe. The atoms in your body were created in ancient stars that lived and died before the sun was born. Heavy elements like carbon, nitrogen, oxygen, and iron were forged in the cores of massive stars and scattered into space when those stars exploded as supernovae. These enriched clouds of gas and dust later collapsed to form new stars and planets, including our solar system about 4.6 billion years ago. The hydrogen in your body is even older, dating from the first few minutes after the Big Bang, when the universe was hot enough for nuclear reactions to occur freely. This hydrogen has remained mostly unchanged since then, drifting through space, becoming part of stars and planets and living things, but always retaining its fundamental nature as the simplest and most abundant element in the universe. You are, quite literally, made of stardust, composed of matter that has cycled through multiple generations of stars and existed across most of the age of the universe. The matter in your body is nearly as old as time itself, and it will continue to exist long after your current form has returned to the cosmic recycling process. From where you are, you exist not only in space, but also in time. You live 13.8 billion years after the Big Bang, on a planet 4.6 billion years old, in a solar system orbiting a star that will shine for another 5 billion years before expanding into a red giant and eventually becoming a white dwarf. You live in an era when the universe is still full of stars, still forming new stars, still containing abundant gas and dust for continued creation. This will not always be the case. In the far future, measured in trillions of years, the universe will expand to the point where galaxies become isolated from each other, separated by such vast distances that light from one can never reach another. Star formation will slow and eventually cease as gas is used up. Existing stars will age and die, until the universe is populated only by cooling remnants, white dwarfs, neutron stars, and black holes. Even these will eventually fade or evaporate over timescales so long they are almost incomprehensible. The universe will become dark and cold, approaching but never quite reaching absolute zero. But that is unimaginably far in the future. In the present, from where you are, the universe is vibrant and dynamic. Stars are being born in nebulae, regions of gas and dust where gravity is pulling material together. These stellar nurseries glow with the light of young, hot stars and the fluorescence of heated gas. The Orion Nebula, visible to the unaided eye as a fuzzy patch in the constellation Orion, is one such region, located about 1,350 light-years away. In the Orion Nebula, hundreds of stars are forming right now, though right now is complicated by the 1,350-year light travel time. New planetary systems are developing around these young stars. Somewhere in that nebula, there may be planets forming that will, billions of years from now, harbor life that looks up at its own sky and wonders about the universe, just as you are doing from your current position. Stars come in many varieties, classified by their temperature, size, and luminosity. The coolest stars are red dwarfs, small stars that burn their fuel very slowly and can live for trillions of years. The hottest stars are blue giants and supergiants, massive stars that burn brilliantly but briefly, living only millions of years before exploding as supernovae. Our Sun is a yellow dwarf, a medium-sized star with a moderate temperature and a lifespan of about 10 billion years. The color of a star tells you its surface temperature. Red stars are coolest, with surface temperatures around 3,000 degrees Fahrenheit. Yellow stars like our Sun are hotter, around 10,000 degrees Fahrenheit. Blue stars are hottest, with surfaces reaching 20,000 degrees or more. These temperatures are measured on the Kelvin scale by astronomers, where absolute zero is 0 Kelvin, but the Fahrenheit equivalents help convey the enormous heat involved. Stars are powered by nuclear fusion, a process that combines light elements into heavier ones, releasing tremendous energy in the process. In the core of the Sun, hydrogen atoms are fused together to create helium, converting about 4 million tons of matter into energy every second. This energy works its way out from the core, taking thousands of years to reach the surface, where it is finally radiated into space as light and heat. The light that reaches Earth from the Sun left the Sun's surface about 8 minutes before it arrived. This means that if the Sun were to suddenly vanish, we would not know for 8 minutes, because that is how long it takes for light to cross the 93 million mile distance. Similarly, if you could somehow observe Earth from the Sun, you would see Earth as it was 8 minutes ago. This delay affects everything we observe in the universe. The Moon's light is actually reflected sunlight, and it takes about 1.3 seconds for light to travel from the Moon to Earth, so you see the Moon as it was 1.3 seconds ago. The outer planets are tens of minutes to hours away in light travel time. Even within your immediate surroundings, light takes time to travel, though at such small distances, the time is immeasurably small for human perception. Light crosses a typical room in a few billionths of a second. The speed of light in a vacuum is exactly 299,792,458 meters per second, usually rounded to 300 million meters per second, or 186,000 miles per second. This speed is not just fast, it is the fastest that anything can possibly travel according to our current understanding of physics. It is a fundamental constant of the universe, the same in all reference frames, regardless of how the source or observer is moving. This universal speed limit has profound implications. It means that information cannot travel faster than light, which prevents certain paradoxes and helps maintain causality in the universe. It also means that the farther away something is, the longer ago we see it, creating that look-back time effect. And it means that the observable universe has a limit, beyond which we cannot see, because light from those regions has not had time to reach us. From your position, you are connected to the observable universe by light. Every photon that enters your eye has traveled from somewhere, carrying information about distant stars, galaxies, or nearby objects. These photons were created by various processes: thermal radiation from hot objects, emission from excited atoms, reflection from surfaces, and many others. Each photon is a tiny packet of electromagnetic energy, having both wave-like and particle-like properties. The electromagnetic spectrum includes much more than visible light. In order of decreasing energy, it includes gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, and radio waves. All of these are fundamentally the same phenomenon, electromagnetic radiation, differing only in wavelength and frequency. Your eyes are sensitive only to a tiny sliver of this spectrum, the visible range from red to violet. Other forms of life on Earth see different parts of the spectrum. Some insects can see ultraviolet light, which helps them find flowers that have UV reflecting patterns invisible to humans. Some snakes can detect infrared radiation, allowing them to sense the heat of warm-blooded prey in darkness. Throughout the universe, objects emit radiation across the entire spectrum, and astronomers use instruments sensitive to all these different wavelengths to study the cosmos. Radio waves from space were first detected in the 1930s, opening up radio astronomy as a new field. Radio telescopes can observe through clouds and interstellar dust that block visible light, revealing structures and phenomena invisible to optical telescopes. Pulsars, rapidly rotating neutron stars that emit beams of radio waves, were discovered using radio telescopes. The cosmic microwave background radiation, was discovered with radio instruments, and radio observations have mapped the distribution of hydrogen gas throughout our galaxy and beyond. Infrared astronomy reveals objects that are too cool to emit much visible light, but still radiate heat. This includes cool stars, planets, dust clouds, and even distant galaxies whose light has been redshifted into the infrared by the expansion of the universe. Infrared observations can penetrate dust clouds, allowing astronomers to see into stellar nurseries and the centers of galaxies. Ultraviolet astronomy requires space-based telescopes because Earth's atmosphere absorbs most UV radiation, protecting life on the surface from its damaging effects. UV observations reveal hot stars, active galactic nuclei, and other energetic phenomena. X-ray and gamma-ray astronomy also require space-based instruments and study the most extreme environments in the universe: black holes, neutron stars, supernova remnants, and the hot gas in galaxy clusters. From where you are, all of this radiation is passing by constantly. Radio waves from distant quasars, infrared from cooling dust clouds, ultraviolet from hot stars, X-rays from matter falling into black holes. All of it streams through space, most of it passing unnoticed unless a detector is placed in its path. You are immersed in electromagnetic radiation from the universe, a silent testament to countless processes occurring at vast distances. The universe is not static. It is changing constantly, though most changes occur on timescales too long or too short for human perception during a lifetime. Stars are born, live, and die, but stellar lifetimes are measured in millions or billions of years. Galaxies merge and evolve, but these processes take hundreds of millions to billions of years. On the other end of the timescale, subatomic particles are created and destroyed in tiny fractions of a second, interactions that underpin the stability of matter but occur too rapidly to observe directly. Some changes in the universe are dramatic and visible even across cosmic distances. Supernovae, the explosive deaths of massive stars, can briefly outshine entire galaxies, becoming visible from billions of light years away. These explosions scatter heavy elements into space, enriching the interstellar medium and providing the raw materials for future stars and planets. They also leave behind compact remnants, neutron stars or black holes, the collapsed cores of the exploded stars. Neutron stars are extraordinarily dense, with masses comparable to the Sun compressed into spheres only about 12 miles across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Some neutron stars rotate rapidly, hundreds of times per second, and emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we detect regular pulses, hence the name pulsars. Black holes, as mentioned earlier, are even more extreme. A stellar mass black hole formed from a collapsing star might have a mass 10 to 20 times that of the Sun, compressed into an infinitely small point. The event horizon, the boundary beyond which nothing can escape, would be just a few dozen miles across. Despite science fiction portrayals, black holes do not actively suck in matter from a distance. Their gravity behaves like any other massive object, unless you get very close to the event horizon. From where you are, the nearest known black hole is probably several thousand light-years away, posing no danger whatsoever to Earth. Black holes are scattered throughout the galaxy, the remnants of ancient massive stars, but space is so vast that encounters are extraordinarily unlikely. The galaxy itself has a structure that reflects its history. The disk contains younger stars and active star formation, with spiral arms where density waves compress gas and trigger new stellar births. The central bulge contains older stars in a more spherical distribution. Surrounding the visible galaxy is a halo of old stars in globular clusters, ancient collections of hundreds of thousands of stars bound tightly together by gravity. Globular clusters are among the oldest objects in the galaxy, with ages of 12 to 13 billion years, almost as old as the universe itself. They formed early in the galaxy's history, and their stars have orbited the galactic center billions of times since then. Some globular clusters are visible to the unaided eye as faint fuzzy stars. The cluster Omega Centauri, for example, appears as a hazy fourth magnitude star in the southern sky, but is actually a sphere of about 10 million stars located about 16,000 light-years away. The galaxy also contains dark matter, a mysterious substance that does not emit, absorb, or reflect light, but reveals its presence through gravitational effects. Observations of how stars orbit in galaxies show that there must be far more mass present than we can see in the form of stars, gas, and dust. This unseen mass is called dark matter, and it appears to make up about 85% of the matter in the universe. We do not know what dark matter is made of. It cannot be normal atoms because we can account for all the normal matter through various observations. Dark matter might be composed of exotic particles that interact with normal matter only through gravity, or it might be something even stranger. Experiments around the world are searching for dark matter particles, trying to detect them directly or create them in particle accelerators, but so far dark matter remains one of the great unsolved mysteries of cosmology. Dark energy is an even deeper mystery. Observations show that the expansion of the universe is accelerating, meaning that distant galaxies are receding faster now than they were in the past. This acceleration requires some form of energy permeating space itself, pushing everything apart. This hypothetical energy is called dark energy, and it appears to make up about 68% of the total energy content of the universe. Normal matter, the atoms that make up stars, planets, and people, accounts for less than 5% of the universe's total energy content. Everything we can see and touch, all the structures we observe, all the light we detect, comes from this small fraction of the cosmic whole. The rest is dark matter and dark energy, unseen and poorly understood. From where you are surrounded by this dark matter and dark energy. They do not interact with you in any noticeable way, except through their gravitational effects on the large-scale structure and expansion of the universe. You are sitting in a sea of dark matter particles, if that is indeed what dark matter is, passing through you without effect, as invisible and intangible as ghosts. Despite these mysteries, we have learned an enormous amount about the universe through patient observation and careful reasoning. The scientific method, applied over centuries, has revealed the structure of the solar system, the nature of stars, the existence of galaxies, the expansion of the universe, and the processes that govern cosmic evolution. This knowledge was built gradually, each generation adding to the work of the previous ones, correcting errors, refining measurements, and developing new theories to explain observations. Ancient astronomers tracked the motions of the sun, moon, and planets, developing calendars and models of the cosmos. They believed Earth was the center of everything, with celestial objects moving in perfect circles around us. This geocentric model worked reasonably well for predicting planetary positions, though it required increasingly complex modifications to match observations. In the 1600s, this view was overturned. Observations by Galileo, Kepler, and others showed that the planets orbit the Sun, not Earth, and that planetary orbits are ellipses, not circles. This heliocentric model, with the Sun at the center of the solar system, was a revolutionary shift in understanding. It removed Earth from its privileged position and showed that we inhabit one planet among several, all orbiting an ordinary star. Later, in the 1700s and 1800s, astronomers realized that stars are distant suns, not lights fixed to a celestial sphere. The Milky Way was recognized as a vast collection of stars, though its true size and nature remained unclear. The discovery of galaxies beyond the Milky Way in the early 1900s expanded our view even further, showing that the universe contains countless separate galaxies, each a vast city of stars. The expansion of the universe, discovered in the 1920s, led to the development of the Big Bang theory in the mid-20th century. The discovery of the cosmic microwave background in the 1960s provided strong support for this theory. More recent observations including detailed maps of the cosmic microwave background and surveys of distant supernovae, have refined our understanding of the universe's age, composition, and fate. All of this knowledge comes from light, from electromagnetic radiation arriving at Earth after journeys lasting from seconds to billions of years. By analyzing this light, astronomers can determine the temperature, composition, velocity, distance, and many other properties of cosmic objects. Spectroscopy, the study of how light is distributed across different wavelengths, is particularly powerful. Each element produces a unique pattern of spectral lines, like a fingerprint, allowing astronomers to determine what distant objects are made of. The same physical laws that operate here on Earth apply throughout the universe. The gravity that holds you to Earth's surface is the same force that holds the Moon in orbit, the planets around the Sun, the solar system in the galaxy, and galaxies in clusters. The nuclear forces that bind atomic nuclei together operate the same way in the Sun as in terrestrial matter. The electromagnetic force that governs chemistry and molecular bonds works identically across cosmic distances. This universality of physical law is one of the most profound and surprising discoveries of science. There is no reason a priori why the universe should operate according to consistent mathematical rules, but it does. This allows us to understand distant phenomena by studying similar processes nearby, and to make predictions about what we will find when we explore new realms. From your current position, you have access to the same universe that astronomers study with their telescopes. The sky you see contains the same stars, the same moon, the same planets. The difference is in the tools used to observe and the knowledge used to interpret what is seen. But the fundamental connection between observer and cosmos is the same whether you are looking with unaided eyes, with binoculars, with a backyard telescope, or with the Hubble Space Telescope. The Hubble Space Telescope, launched in 1990 and still operating today, has provided some of the most detailed and beautiful images of the cosmos ever obtained. Free from the blurring effects of Earth's atmosphere, Hubble can resolve fine details in distant galaxies, observe faint objects, and capture views across the electromagnetic spectrum from near-infrared to ultraviolet. Hubble's successor, the James Webb Space Telescope, launched in 2021, operates primarily in the infrared and can see even farther and fainter objects, peering into the dusty regions where stars are born and looking back to the earliest galaxies in the universe. These instruments extend human vision across space and time, allowing us to explore the universe in ways impossible from the ground. But they are still fundamentally doing the same thing you do when you look up at the night sky, collecting light and using it to learn about what is out there. The universe from where you are right now extends from the subatomic to the cosmic, from the quantum foam possibly underlying space-time itself, to the vast superclusters of galaxies spanning hundreds of millions of light-years. You exist in the middle of this range of scales, at a size where you can contemplate both the very small and the incomprehensibly large. An atom is about 1/10,000,000th of a meter across. Your body contains roughly 7 octillion atoms, a 7 followed by 27 zeros. Each of these atoms consists of a nucleus containing protons and neutrons, surrounded by a cloud of electrons. The nucleus is 100,000 times smaller than the atom itself, meaning that atoms are mostly empty space. If an atom were enlarged to the size of a football stadium, the nucleus would be like a marble at the center, with electrons as tiny specks orbiting near the outer walls. Yet this mostly empty structure is what gives matter its solidity. The electromagnetic forces between atoms, particularly the repulsion between electron clouds, prevent objects from passing through each other. When you sit in a chair, you are not truly touching it in the sense of atoms making contact. Rather, the electron clouds in your body and the chair repel each other with enough force to support your weight, maintaining a tiny gap at the atomic scale. Protons and neutrons are themselves made of even smaller particles called quarks, bound together by the strong nuclear force. Quarks have never been observed in isolation. They are always confined within particles like protons and neutrons. Electrons, as far as we know, are fundamental particles with no internal structure, though they are governed by the laws of quantum mechanics, which describe a realm of probability and uncertainty, unlike anything in everyday experience. Quantum mechanics reveals that at the smallest scales, particles do not have definite positions and velocities simultaneously. Instead, they exist in superpositions of multiple states, only taking on definite properties when measured. This is not due to limitations in our measurements, but appears to be a fundamental feature of reality. Particles can exhibit wave-like behavior, and light can exhibit particle-like behavior, a duality that seems paradoxical but is well established experimentally. The implications of quantum mechanics are still being explored and debated. Some interpretations suggest that observation itself plays a fundamental role in determining reality. Others propose that all possible outcomes of quantum events actually occur, but in separate branching universes. Still, others maintain that quantum mechanics is simply a mathematical tool that predicts observations without necessarily describing an underlying reality. These interpretations differ in their philosophy, but agree on the mathematics and the predictions, which have been confirmed in countless experiments. From your position in the hierarchy of scales, looking down toward the quantum realm reveals a strange and unfamiliar world. Looking up toward the cosmic realm reveals vastness beyond human intuition. Both directions lead to realms that challenge our everyday understanding of how things work. The cosmic realm operates on scales of space and time that dwarf human experience. The nearest star is 4.24 light-years away, which is about 25 trillion miles. Even at the speed of light, unreachable by any material object, it would take over 4 years to get there. With current technology, it would take tens of thousands of years to reach even this nearest star. The fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour as it swings close to the Sun. At this speed, it would still take more than 6,000 years to reach Proxima Centauri. Our exploration of space has been limited to our immediate neighborhood, the Moon a few days away, and robotic probes to the outer planets, which take years to arrive. Voyager 1, launched in 1977, is currently the most distant human-made object, over 14 billion miles from Earth and counting. It is traveling at about 38,000 miles per hour relative to the Sun, but even at this speed, it would take over 70,000 years to reach the distance of the nearest star, if it were headed in that direction, which it is not. These distances illustrate the challenge of interstellar travel. Even if we could somehow travel at a significant fraction of the speed of light, journeys to other stars would take years at minimum, and more likely decades or centuries for more distant destinations. The energy required for such journeys is enormous, far beyond current technological capabilities. This has not stopped us from thinking about the possibility. Scientists and engineers have proposed various concepts for interstellar travel: fusion rockets, antimatter propulsion, laser-driven light sails, generation ships, and even more speculative ideas like warp drives or wormholes. None of these is currently feasible, but they represent the human drive to explore, to reach beyond our current limits. For now, our exploration of the universe beyond the solar system is limited to remote observation. We send electromagnetic radiation outward and collect electromagnetic radiation arriving from space. Radio and optical telescopes serve as our eyes and ears, gathering information from across the cosmos. Some of the radiation we have sent out intentionally, in the form of radio messages directed at nearby stars, attempts to communicate with any intelligent life that might be listening. These messages contain information about humanity, Earth, and our location in the galaxy. They travel at the speed of light, and if there is anyone there to receive them, a reply would take at least twice the distance in years to arrive. We also listen for signals from other civilizations, using radio telescopes to scan the sky for patterns that might indicate artificial origin. This effort, known as the Search for Extraterrestrial Intelligence, or SETI, has been ongoing for decades, but has not yet found convincing evidence of alien technology. This does not mean such evidence does not exist, only that we have not found it in the tiny fraction of the sky we have been able to search with sufficient sensitivity. The question of whether life exists elsewhere in the universe is one of the most profound we can ask. We know life exists here on Earth, having arisen sometime in the first billion years of Earth's history, perhaps 3.8 billion years ago. Life has persisted and evolved ever since, adapting to changing conditions, surviving mass extinctions, and eventually giving rise to complex organisms, including humans. The conditions that allowed life to arise on Earth are not unique. Many stars have planets, and many of those planets are in the habitable zone where liquid water could exist on the surface. The elements necessary for life as we know it, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are common throughout the universe. The chemical reactions that led to the first living things presumably followed the same physical laws that operate everywhere. All of this suggests that life should be common in the universe, perhaps even inevitable on suitable planets. Yet we have no confirmation of life beyond Earth. This discrepancy is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a discussion about extraterrestrial civilizations. There are many possible answers to this question. Perhaps life is common but intelligent. Technological life is rare. Perhaps intelligent life is common, but tends to destroy itself before reaching a stage where interstellar communication or travel is possible. Perhaps civilizations are common but quiet, not broadcasting their presence. Perhaps the universe is teeming with life, but the distances are so vast that contact is incredibly unlikely. Or perhaps we are in fact alone, the only instance of life in an enormous, otherwise sterile universe. We do not yet know the answer, and this uncertainty is part of what makes the question so compelling. Every observation of a potentially habitable planet, every experiment on the origin of life, every SETI search brings us incrementally closer to an answer, even if that answer is a negative result. From where you are, the possibility of other life in the universe is just that, a possibility. It is neither confirmed nor ruled out. Earth remains the only known abode of life, a pale blue dot in the vastness of space, unique in its ability to harbor living things, at least as far as our current knowledge extends. This uniqueness, or potential uniqueness, gives Earth and its life special significance. Whether we are alone or one of countless inhabited worlds, the life here is precious, the result of billions of years of evolution, adaptation, and chance. The diversity of life on Earth, from microbes to whales, from fungi to trees, represents a vast experiment in what is possible when chemistry, energy, and time come together in the right way. Your own existence is part of this story. You are a member of the species Homo sapiens, which evolved in Africa roughly 300,000 years ago. Your species spread across the globe, developed language, culture, art, and technology, and eventually gained the ability to look beyond Earth and understand its place in the universe. This understanding has developed remarkably quickly in cosmic terms. For most of human history, the nature of the stars, the size of the Earth, and the structure of the solar system were unknown. It has only been in the last few centuries that we have pieced together an accurate picture of the cosmos, and only in the last century that we have understood the immense scale and age of the universe. You live in a privileged time, when humanity has gained enough knowledge to understand the universe in broad strokes, but still faces enough mysteries to make exploration exciting. Future generations may have answers to questions we can barely formulate today, just as we have answers to questions that would have seemed impossible to answer in previous centuries. The universe from where you are is both knowable and mysterious. We have learned an enormous amount, but each answer raises new questions. We know the universe is expanding, but we do not fully understand dark energy. We know galaxies form and evolve, but the details of these processes are still being worked out. We know the fundamental forces of nature, but we do not have a complete theory that unifies them all. One of the biggest gaps in our knowledge is the lack of a theory that combines quantum mechanics and gravity. Quantum mechanics describes the very small, and general relativity describes gravity and the very large. But these two theories are mathematically incompatible. Attempts to create a theory of quantum gravity have led to ideas like string theory and loop quantum gravity, but none has yet been confirmed experimentally. This incompatibility becomes important in situations where both quantum mechanics and gravity are significant, such as the interior of black holes or the earliest moments of the Big Bang. In these extreme conditions, our current theories break down, and we need a more complete description of physics to make predictions. Despite these gaps, the amount we do understand is staggering. We can describe the life cycle of stars, the formation of galaxies, the creation of elements, and the overall evolution of the universe from the Big Bang to the present. We can predict the positions of planets, the timing of eclipses, and the behavior of spacecraft with extraordinary precision. We can look back in time by observing distant light and forward in time by applying physical laws to current conditions. From where you are, all of this knowledge is accessible. It exists in books, scientific papers, online resources, planetarium shows, and countless other forms. Human knowledge has become remarkably democratized, especially with the advent of the internet. Questions that once required access to specialized libraries or experts can now be answered in moments with a search query. This accessibility of knowledge is a recent development and a powerful one. It allows anyone with curiosity to explore the universe without leaving home, to learn about stars and galaxies, atoms and forces, the history of the Earth and the evolution of life. It connects you to a tradition of inquiry that extends back thousands of years, to the earliest humans who looked up at the night sky and wondered what those lights were. Those ancient observers created myths and stories to explain the heavens. They saw patterns in the stars and imagined gods, heroes, and beasts. These stories served important cultural functions, connecting people to their environment and to each other, providing frameworks for understanding the world. Modern science has replaced these myths with a different kind of story, one based on observation, experiment, and mathematical reasoning. This scientific story is not complete and never will be, as there will always be more to discover. But it has the virtue of being testable, self-correcting, and increasingly accurate. The scientific story tells us that the universe began in a hot, dense state and has been expanding and cooling ever since. It tells us that stars are born in clouds of gas and dust, live by fusing elements in their cores, and die in various ways depending on their mass. It tells us that planets form from the leftover material around young stars, and that at least one of those planets has given rise to life. This story is grand in scope, but also personal. It tells you where you came from, what you are made of, and how you fit into the larger cosmos. You are a temporary arrangement of atoms, organized in a way that allows self-awareness and contemplation. Your atoms will eventually return to the environment, be incorporated into other structures, and continue the cosmic cycle. This cycle has been ongoing for billions of years and will continue for billions more. The universe is not static, but constantly changing, with old structures dying and new ones being born. You exist in one particular moment of this vast process, a moment that will seem no different in cosmic terms from any other, but which is unique from your perspective because it is the moment you are alive. From where you are right now, you can reflect on all of this. You can think about your place in space, from the room you occupy to the planet, solar system, galaxy, and observable universe. You can think about your place in time, from the present moment back to the Big Bang and forward to whatever future awaits. You can consider the atoms in your body, their nuclear origins, and their eventual fate. This contemplation can be humbling, making you aware of how small and brief your existence is compared to the cosmos. It can also be empowering, showing you that you are part of something vast and ancient, connected to everything else through the laws of physics and the history of matter. The universe from where you are is a universe of connections. Everything influences everything else through gravity, electromagnetic forces, and the other fundamental interactions. The Earth's gravity holds you to the surface, the Moon's gravity raises tides, the Sun's gravity holds the solar system together, and the galaxy's gravity binds hundreds of billions of stars in a slowly rotating disk. These connections extend across space and time. The light you see from a distant star connects you to that star, carrying information across the intervening space. The atoms in your body connect you to ancient stars, your elemental ancestry written in the periodic table. Your thoughts and observations connect you to the same universe that has been contemplated by countless others throughout history. This web of connections means that you are not separate from the universe, but part of it. You are not merely in the universe. You are made of it, shaped by it, and connected to it at every level. The boundary between you and the universe is somewhat arbitrary, a product of perception rather than any fundamental division. Recognizing this unity can change how you think about your relationship with the cosmos. Instead of being a tiny, isolated being in a vast, indifferent universe, you are an integral part of the whole, as much a feature of the universe as a star or galaxy. The universe has given rise to you through physical processes operating over billions of years, and through you the universe becomes aware of itself. This self-awareness of the cosmos through conscious beings may be rare or common in the universe. We do not know, but it is certainly remarkable. Through observation and thought, matter that was once diffuse, hydrogen gas has become organized in a way that allows it to contemplate its own existence and origins. This is one of the most astonishing outcomes of cosmic evolution. From your current position, you have the opportunity to participate in this cosmic self-awareness. By learning about the universe, thinking about its nature, and sharing that understanding with others, you contribute to humanity's collective knowledge and appreciation of the cosmos. This is a privilege and a responsibility, one that connects you to past and future generations of observers and thinkers. The universe will continue regardless of whether anyone pays attention to it. Stars will be born and die, galaxies will merge, and the expansion will continue. But the meaning we find in these processes, the beauty we perceive in cosmic structures, and the understanding we develop through investigation, these are human contributions, adding a layer of significance to the physical unfolding of events. Where you are right now is both a specific location in space and time, and a perspective on the universe. The location is temporary. You will move and eventually your atoms will be redistributed, but the perspective, the ability to observe and contemplate, is part of the ongoing story of how the universe experiences itself. This perspective is shaped by your biology, your culture, your education, and your personal experiences. No two people see the universe exactly the same way, because no two people have exactly the same combination of these factors. Yet there is enough commonality, enough shared perception and reasoning, that we can communicate about what we observe and build collective understanding. Science is the systematic application of this collective understanding. It is a method for investigating the world that relies on observation, experimentation, and logical reasoning, with results that can be verified by others. Science is self-correcting, as new observations can overturn old theories, and it is cumulative, with each generation building on the work of previous ones. Through science, humanity has mapped the Earth, explored the solar system, probed the atom, decoded the genome, and traced the history of the universe. These achievements represent some of the finest work of human intellect and collaboration. They also represent an ongoing process, as there is always more to learn, more to discover, more to understand. From where you are, you have access to the fruits of this process. You can learn what has been discovered, understand how we know what we know, and even contribute to the endeavor yourself if you choose. The barriers to participation are lower than ever before. With information freely available, and tools for observation and analysis more accessible than in any previous era. This democratization of science and knowledge is one of the great achievements of modern civilization. It means that curiosity, rather than privilege, can be the main requirement for learning about the universe. Anyone who wants to understand the cosmos can find resources to help them, from books and websites to courses and documentaries. The universe from where you are is the same universe that everyone else inhabits, but your experience of it is unique. The angle from which you view the night sky, the specific stars visible from your latitude, the light pollution or clear darkness of your location, the season and time of night, all these factors affect what you can see. But beyond these specifics, you share access to the same cosmos as anyone else who looks up. This shared cosmos is a unifying factor for humanity. Regardless of differences in culture, language, nationality, or belief, we all live under the same sky, orbit the same sun, and exist in the same universe. The laws of physics that govern our world operate equally everywhere. The stars shine for everyone. The expansion of the universe carries all galaxies along together. Recognizing this common context can foster a sense of connection and shared fate. The challenges humanity faces, from climate change to resource management to the risks of nuclear war, are species-level issues that affect everyone. Similarly, the triumphs of human achievement, like curing diseases, creating art, or exploring space, are accomplishments that belong to all of us. From where you are right now, you are a participant in human civilization at a particular moment in its development. You inherit the knowledge, culture, and technology of those who came before, and you will pass on something to those who come after, even if only in small ways. Your existence is part of the larger human story, which is itself part of the larger story of life on Earth, which is part of the story of the solar system, which is part of the story of the galaxy, which is part of the story of the universe. These nested stories all connect to each other. The history of the universe sets the stage for the formation of galaxies, which sets the stage for the formation of stars and planets, which sets the stage for the development of life, which sets the stage for the evolution of intelligence, which leads to beings capable of understanding their place in the cosmos. This understanding has practical value as well as philosophical significance. Knowing about the universe helps us navigate it, predict events, develop technologies, and answer questions about our origins and future. It also enriches our lives, providing a sense of wonder, beauty, and connection to something larger than ourselves. The beauty of the cosmos is undeniable. From the intricate patterns of spiral galaxies to the delicate colors of nebulae, from the perfect circle of the full moon to the subtle dance of planets against the background stars, the universe offers countless examples of visual splendor. These are not beauties created for our benefit. They are simply the natural outcomes of physical processes. Yet we find them beautiful nonetheless, perhaps because we have evolved to recognize pattern and symmetry, or perhaps for deeper reasons we do not fully understand. This beauty is accessible from where you are. You do not need a telescope to appreciate the elegance of the night sky, though optical aid certainly enhances the experience. You do not need to understand the physics to feel wonder at the vastness of space, though understanding can deepen that wonder. The universe presents itself to anyone who takes the time to look, offering an experience that is at once humbling and uplifting. From your current position, the act of looking up and out connects you to a tradition of sky watchers extending back to the earliest humans. Those ancient observers may not have understood what they were looking at, but they looked nonetheless, finding meaning and inspiration in the heavens. You continue that tradition, informed by modern knowledge but motivated by the same curiosity and wonder. This chapter has explored the universe from where you are, starting with your immediate surroundings and expanding outward through the solar system, the galaxy, and beyond. It has covered your place in space from local to cosmic scales and touched on your place in time, from the present moment back to the origin of the universe. The next chapter will delve deeper into specific phenomena and objects in the universe, exploring in greater detail the nature of stars, galaxies, and exotic objects like black holes and neutron stars. It will maintain the same calm, informative tone, providing you with a comprehensive understanding of the cosmos, while remaining gentle and conducive to relaxation. As you continue this journey of cosmic exploration, remember that all of this exists around you right now. The universe is not somewhere else. It is here and you are in it, an integral part of the whole. Every breath you take is made possible by cosmic processes that created the air you breathe. Every thought you think occurs in a brain built from stardust. You are the universe experiencing itself, and that is a remarkable thing. Stars are the fundamental building blocks of the visible universe. They light up the cosmos, create heavy elements, and provide the energy that makes life possible on planets like Earth. Understanding stars means understanding much of what we observe in the night sky, and the processes that govern stellar life reveal deep truths about how the universe works. A star begins its life in a nebula, which is a cloud of gas and dust floating in interstellar space. These clouds can be enormous, spanning dozens or even hundreds of light years across, and containing enough material to form thousands or millions of stars. The gas in these nebulae is mostly hydrogen, the simplest and most abundant element in the universe, mixed with smaller amounts of helium and trace quantities of heavier elements. A nebula can exist peacefully for millions of years, with its gas spread thinly through space, held together loosely by its own gravity. But sometimes, something disturbs this equilibrium. The disturbance might be a shock wave from a nearby supernova explosion, the gravitational influence of a passing star, or the collision of two gas clouds. Whatever the cause, the disturbance compresses part of the nebula, increasing its density. When gas is compressed, its own gravity becomes stronger in that region. This creates a feedback loop. Gravity pulls more gas inward, which increases the mass and strengthens the gravity further, which pulls in even more gas. This process is called gravitational collapse, and it is the mechanism by which stars are born. As the collapsing region contracts, it heats up. This might seem counterintuitive, but it is a consequence of the laws of thermodynamics. When gas is compressed, the particles move faster on average, and temperature is a measure of this average particle motion. The collapsing cloud fragment becomes warmer as it becomes smaller and denser. This collapse does not happen instantaneously. For a cloud fragment that will eventually become a star like our Sun, the collapse takes roughly 50 million years. During this time, the fragment evolves from a diffuse cloud to a dense core surrounded by a rotating disk of material. This disk is important because it is from this disk that planets will eventually form, though that is a later stage of the process. At the center of the collapsing fragment, the density and temperature continue to increase. The core becomes so dense that it is opaque, trapping heat inside. The temperature rises to thousands, then tens of thousands, then hundreds of thousands of degrees. The material is no longer a gas in the ordinary sense, but a plasma, where electrons have been stripped from atoms by the intense heat, creating a mixture of free electrons and atomic nuclei. When the core temperature reaches about 10 million degrees Kelvin, something remarkable happens. At these temperatures, hydrogen nuclei, which are just single protons, are moving so fast that when they collide, they can overcome the electromagnetic repulsion between them. Protons are positively charged, and like charges repel, normally preventing nuclei from getting close enough to interact. But at 10 million degrees, the thermal energy is sufficient to bring protons close enough that the strong nuclear force can take over. The strong nuclear force operates at very short ranges, less than the diameter of a proton, but within that range, it is much more powerful than the electromagnetic force. When two protons get close enough, the strong force binds them together, though the process is complex and requires several steps. The end result is that 4 hydrogen nuclei are fused together to form one helium nucleus, releasing energy in the process. This energy release is what powers a star. The fusion of hydrogen into helium converts a small amount of mass into energy, following Einstein's famous equation E equals mc squared. The amount of mass converted is tiny for each reaction, but stars contain enormous amounts of hydrogen, and fusion reactions occur at staggering rates. In the Sun, about 600 million tons of hydrogen are converted into helium every second, with about 4 million tons of that mass converted into pure energy. This energy is released primarily as gamma rays, which are high-energy photons. These photons immediately collide with nearby particles in the dense stellar core, transferring their energy and being absorbed and re-emitted countless times. Each interaction degrades the photon's energy slightly, shifting it to longer wavelengths. Over many thousands of years, the energy from fusion reactions in the core gradually works its way outward through the star, being absorbed and re-emitted countless times. By the time this energy reaches the star's surface, the gamma rays from the core have been degraded into visible light, infrared radiation, and other forms of electromagnetic energy. This light streams into space, and if the star happens to be our Sun, some of it travels 93 million miles to Earth, where it provides the energy for life and allows you to see the world around you. The outward pressure from this energy radiation balances the inward pull of gravity, creating a stable equilibrium. A star in this balanced state is said to be on the main sequence, which is the long, stable phase of a star's life during which it fuses hydrogen into helium in its core. The Sun has been on the main sequence for about 4.6 billion years and will remain there for another 5 billion years or so. The lifetime of a star on the main sequence depends critically on its mass. More massive stars have more fuel, which might suggest they would live longer, but the opposite is true. More massive stars have stronger gravity, which requires higher core temperatures to maintain equilibrium. Higher temperatures mean faster fusion rates, so massive stars burn through their fuel much more quickly than smaller stars. A star with 10 times the Sun's mass might live only 20 million years on the main sequence. A star with 50 times the Sun's mass might live only a few million years. These may seem like long times by human standards, but they are brief compared to the age of the universe. At the other end of the scale, a star with 1/10 the Sun's mass might live for 1 trillion years, far longer than the current age of the universe. This means that all the very massive stars that have ever existed have already died. When you look at the night sky, every blue giant star you see is a young star, probably only millions of years old, because such stars cannot be old. They burn brilliantly but briefly, like cosmic fireworks. Conversely, the faint red dwarf stars, which are difficult or impossible to see with the unaided eye, are the real survivors of the galaxy. Some of them formed when the galaxy was young and will still be shining trillions of years from now. Our Sun is intermediate in both mass and lifespan. It is neither the brightest nor the faintest, neither the longest lived nor the most ephemeral. It is, in many ways, an average star, which is perhaps fortunate for us. A more massive star would have burned out long before life could evolve on Earth. A less massive star would provide less energy, potentially making it harder for life to develop. The Sun's current stable state will not last forever. Eventually, probably in about 5 billion years, the hydrogen in the core will be depleted. At that point, fusion in the core will cease, and the core will no longer produce the outward pressure needed to balance gravity. The core will begin to contract under its own weight. This contraction will heat the core, and eventually the temperature will rise high enough that a shell of hydrogen surrounding the helium core will begin to fuse. This shell burning will release energy, but the structure of the star will change dramatically. The outer layers will expand and cool, and the Sun will become a red giant, a star that is much larger in radius but cooler in surface temperature. As a red giant, the Sun will swell to perhaps 100 times its current diameter, potentially engulfing the inner planets, including possibly Earth. The surface temperature will drop from its current 5800 Kelvin to perhaps 3000 Kelvin. giving the star a reddish appearance. Despite the cooler surface, the total energy output will increase because the surface area will be so much larger. The red giant phase is unstable and relatively short-lived compared to the main sequence. For the Sun, this phase will last perhaps 1 billion years. During this time, the helium ash that accumulated in the core during the main sequence will continue to build up and heat up. Eventually, when the core temperature reaches about 100 million degrees Kelvin, helium fusion will ignite. Helium fusion combines 3 helium nuclei to form 1 carbon nucleus in a process called the triple alpha process. This process also releases energy, though less than hydrogen fusion does per unit mass. Helium burning in the core will stabilize the star temporarily, creating a new equilibrium. The Sun will shrink slightly from its maximum red giant size and settle into a new stable phase. This helium burning phase will last only about 100 million years, much shorter than the main sequence. When the helium in the core is exhausted, the core will again contract and heat, and helium burning will continue in a shell around a carbon-oxygen core. The outer layers will expand again, and the star will become an even larger red giant, sometimes called an asymptotic giant branch star. During this phase, the star will become unstable, pulsating in size and brightness. Strong stellar winds will blow off the outer layers, ejecting a significant fraction of the star's mass into space. These winds will carry with them the carbon and oxygen created by helium fusion, along with whatever heavier elements were present in the star from its formation. Eventually, the outer layers will be completely lost, drifting away into space as an expanding shell of gas. This shell, illuminated by the hot core of the dying star, will glow and create what is called a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. They were named by early observers who thought they looked like the disks of planets when viewed through small telescopes. The core left behind after the outer layers are lost is no longer capable of fusion. It is composed primarily of carbon and oxygen with no source of internal energy. This core is supported not by thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain point. This remnant is called a white dwarf. A white dwarf is extraordinarily dense. The Sun's mass compressed into a sphere about the size of Earth results in a density of roughly 1 million times that of water. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf has no internal energy source, so it simply radiates away its stored heat over billions of years, gradually cooling and fading. Eventually, after trillions of years, a white dwarf will cool to the point where it no longer emits significant visible light, becoming a black dwarf. However, the universe is not yet old enough for any white dwarfs to have cooled to this point. Every white dwarf that exists is still glowing, still slowly radiating its thermal energy into space. This is the fate awaiting our Sun, to become a white dwarf that will slowly cool for trillions of years. It is not a violent end, but a gradual fading away. However, more massive stars meet different fates, and their deaths are far more dramatic. For stars with masses between about 8 and 20 times the Sun's mass, the evolutionary path is similar up to a point. These stars also fuse hydrogen to helium, then helium to carbon and oxygen. But unlike the Sun, they have enough mass and core temperature to continue fusion beyond helium burning. After helium is exhausted in the core contracts and heats further, eventually reaching temperatures where carbon can fuse. Carbon fusion produces neon, magnesium, and other elements. The core continues to contract and heat, and successive fusion stages occur: neon burning, oxygen burning, and finally silicon burning. Each stage produces heavier elements and releases less energy per unit mass than the previous stage. Each stage also occurs more quickly. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts hundreds of years. Oxygen burning lasts months. Silicon burning lasts only days. Silicon burning produces iron, and this is where the process stops. Iron is the most stable nucleus, meaning that fusing iron into heavier elements would require energy input rather than releasing energy. Once the core is primarily iron, no further fusion can occur. The core is essentially a ball of inert iron, growing as silicon burning in a surrounding shell continues to add more iron to it. With no fusion to provide outward pressure, the core is supported only by electron degeneracy pressure, the same quantum effect that supports white dwarfs. However, if the core mass exceeds a limit called the Chandrasekhar limit, about 1.4 times the Sun's mass, even electron degeneracy pressure is insufficient to hold the core up against gravity. When this limit is exceeded, the core collapses catastrophically. The collapse happens in less than a second, with the core shrinking from about the size of Earth to a sphere only 12 miles across. This sudden collapse releases an enormous amount of gravitational potential energy, heating the core to billions of degrees and creating conditions where protons and electrons are forced together to form neutrons. The formation of neutrons is accompanied by the release of neutrinos, nearly massless particles that interact only weakly with matter. An enormous burst of neutrinos floods out from the collapsing core, carrying away most of the energy released by the collapse. A tiny fraction of the energy goes into creating a shockwave that travels outward through the star's outer layers. This shockwave blows the outer layers of the star into space at speeds of tens of thousands of miles per second. The sudden heating from the shockwave also triggers a final burst of nuclear fusion in the outer layers, creating elements heavier than iron, including gold, platinum, uranium, and all the other elements that cannot be created by fusion in stellar cores. This explosion is called a supernova, and it is one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy of billions of stars. The light from a supernova can be seen from billions of light years away, making these events visible across much of the observable universe. Supernovae are important for several reasons. They create and scatter heavy elements, enriching the interstellar medium with the building blocks of planets and life. They produce shockwaves that can trigger the formation of new stars by compressing nearby gas clouds, and they leave behind exotic remnants, neutron stars or black holes. A neutron star is the collapsed core of the star, composed almost entirely of neutrons packed together at nuclear density. A neutron star with about 1.4 times the Sun's mass might be only 12 miles in diameter. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars have extraordinarily strong magnetic fields, trillions of times stronger than Earth's magnetic field. As the star collapses, any magnetic field present is compressed and intensified. These fields can channel particles and radiation into beams that sweep through space as the neutron star rotates. Many neutron stars rotate very rapidly, sometimes hundreds of times per second. This rapid rotation is also a consequence of the collapse. As the core shrinks, conservation of angular momentum causes it to spin faster, much like a figure skater pulling in their arms to spin more rapidly. If the beams of radiation happen to sweep across Earth, we detect regular pulses, and the neutron star is called a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who detected radio pulses arriving at precise intervals. Initially, the regular pulses were so precise that they were jokingly referred to as LGM signals for little green men, before it was realized that they came from a natural astrophysical object. Pulsars are among the most precise clocks in nature. The rotation periods are incredibly stable, varying by only tiny fractions of a second over long periods. Some pulsars have been timed for decades, and their behavior is so predictable that they could potentially be used for navigation in space. Not all neutron stars are pulsars. Some neutron stars do not have beams that point toward Earth, so we do not detect pulses even if the star is rotating. Other neutron stars may have very weak magnetic fields or may have slowed down enough that they no longer emit detectable radiation. These invisible neutron stars are still out there, silent remnants of ancient supernovae, detectable only if they happen to be in binary systems where their gravitational influence affects a companion star. For stars even more massive than those that become neutron stars, roughly above 20 to 25 solar masses, the core collapse produces something even more extreme. If the core mass exceeds about 3 solar masses, not even neutron degeneracy pressure can support it against gravity. The core continues to collapse past the neutron star stage, shrinking without limit until it forms a black hole. A black hole is a region of space-time where gravity is so strong that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon, the boundary of the black hole, can ever escape. The event horizon is not a physical surface, but simply the point of no return. For a non-rotating black hole, the radius of the event horizon is directly proportional to the mass. A black hole with 3 times the Sun's mass would have an event horizon radius of about 5 miles. A black hole with 10 solar masses would have a radius of about 18 miles. Despite science fiction portrayals, black holes are not cosmic vacuum cleaners that suck in everything around them. At a distance, a black hole's gravity is no different from any other object of the same mass. If the Sun were suddenly replaced by a black hole of the same mass, Earth's orbit would not change at all. We would freeze in the absence of sunlight, but we would not be pulled into the black hole. The gravitational influence at Earth's orbital distance would be identical to what it is now. Close to a black hole, however, tidal forces become extreme. Tidal forces arise because gravity weakens with distance. Your feet, being slightly closer to Earth's center than your head, experience slightly stronger gravity. This difference is what causes ocean tides, when the moon's varying gravitational pull distorts Earth's water. Near a black hole, tidal forces become so strong that they would stretch and compress any object dramatically. An unfortunate astronaut falling into a black hole would experience spaghettification, being stretched lengthwise and compressed sideways by the extreme tidal gradients. This would occur before reaching the event horizon for small black holes, though for supermassive black holes, the tidal forces at the event horizon are much weaker, and an astronaut could cross the horizon without immediately noticing anything unusual. Once past the event horizon, escape is impossible. All paths, even those pointed away from the black hole, lead inevitably toward the center. Time and space become distorted in ways described by Einstein's general theory of relativity. To an outside observer, objects falling toward a black hole appear to slow down as they approach the event horizon, taking infinite time to actually cross it. The light from the falling object becomes increasingly red-shifted and dimmer, fading from view. From the perspective of the falling object, however, time proceeds normally, and the event horizon is crossed in finite time. Beyond the horizon, the object continues toward the center, where general relativity predicts a singularity, a point of infinite density and zero volume, where the known laws of physics break down. We do not truly understand what happens at the singularity. Our theories of physics, both general relativity and quantum mechanics, become inadequate in this regime. A complete theory of quantum gravity would be needed to describe what actually exists at the center of a black hole, and we do not yet have such a theory. Black holes can grow by accreting matter from their surroundings. In a binary system, a black hole can pull gas from a companion star. This gas forms an accretion disk, spiraling inward toward the event horizon. As the gas spirals inward, it heats up due to friction and compression, eventually becoming so hot that it emits X-rays. These X-ray binary systems are some of the brightest X-ray sources in the sky, and were among the first ways astronomers detected stellar mass black holes. The gas in an accretion disk can reach temperatures of millions of degrees as it approaches the black hole. It spirals inward faster and faster, eventually crossing the event horizon and disappearing from view. The last stable orbit around a black hole is at 3 times the radius of the event horizon for a non-rotating black hole. Inside this orbit, gas can no longer maintain a circular path and plunges rapidly inward. Black holes can also emit jets, narrow beams of particles and radiation that stream outward from the vicinity of the black hole at nearly the speed of light. These jets are powered by the rotational energy of the accretion disk and the black hole itself, though the exact mechanism is not fully understood. The jets can extend for thousands of light years, creating lobes of emission where they collide with surrounding gas. At the centers of most galaxies, including our own Milky Way, there are supermassive black holes with masses ranging from millions to billions of times the Sun's mass. These are not formed from stellar collapse, but rather grew over billions of years through accretion and mergers. The supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Supermassive black holes influence their entire galaxies. Their gravity affects the orbits of stars in the galactic center, and the energy released by accretion onto these black holes can heat gas and drive powerful outflows that regulate star formation. In some galaxies, the supermassive black hole is actively accreting matter and creating an active galactic nucleus, or AGN, which can outshine all the stars in the galaxy combined. Quasars are the most luminous type of AGN, powered by supermassive black holes, accreting matter at very high rates. Quasars were most common when the universe was younger, several billion years ago, and represent a phase in galaxy evolution when black holes were growing rapidly. Today, most supermassive black holes, including the one in the Milky Way, are relatively quiet, accreting only small amounts of matter and producing minimal radiation. The formation and growth of supermassive black holes is still not fully understood. They were already in place in the early universe, less than 1 billion years after the Big Bang, which suggests they must have formed and grown very rapidly. Various mechanisms have been proposed, including direct collapse of massive gas clouds, growth from seed black holes formed by the first generation of stars, and mergers of smaller black holes. Black holes can merge with each other. When 2 black holes orbit each other, they lose energy by emitting gravitational waves, ripples in space-time itself, predicted by Einstein's general relativity. As energy is lost, the orbit shrinks, and the black holes spiral closer together. Eventually, they merge into a single larger black hole in a violent event that releases more energy in gravitational waves than all the stars in the observable universe emit in light during the same time. Gravitational waves were first directly detected in 2015 by the LIGO observatories, a discovery that opened a new window on the universe. The detected signal came from the merger of 2 black holes about 30 times the Sun's mass each, located about 1.3 billion light-years away. Since then, dozens of black hole mergers, as well as neutron star mergers, have been detected through their gravitational wave emission. Gravitational waves travel at the speed of light and can pass through matter almost unimpeded, unlike light, which can be absorbed or scattered. This means gravitational wave astronomy can potentially observe events that are hidden from electromagnetic observation, such as mergers occurring inside dense gas clouds or in the early universe before stars formed. The study of black holes, neutron stars, and other exotic objects has revealed much about the nature of matter under extreme conditions. These objects push the boundaries of physics, testing our theories in regimes that can never be reproduced in laboratories on Earth. They also connect to broader questions